Hi, everyone. Good afternoon. My name is Caro Campos. I am a tech lead with the Conan team, and I'm based in the UK. And today I'm going to talk about not so much about the features in Conan 2 or what's new in Conan 2, but all the requirements that shape up what Conan is, right? All the challenges that we get from being C++ developers and managing our dependencies. So to start off, I'll talk about what I call developer envy. Very often we'll hear people maybe in social media or newer developers coming from university or with experiences in other languages. Does C++ have a package manager like, and then people will say npm or pip or gem or some other package manager from a different language? We're all very familiar with this. This question actually was, well, this one was asked 8 years ago on Reddit, but there's more recent ones. You'll have people saying, oh, what bothers me about C++ is that the dependency management is not as, sophisticated as Python or Ruby or Node. So this is a recurrent theme, I'm afraid. But as you all are aware, one does not simply just write a C++ package manager, right? So this is, unfortunately for us in the Conan team, this is a very complex problem. So I'm going to first start with a deliberately simple case of a pure Python library and how this is handled by pip currently. So I have just a short snippet of Python code where I am importing the URL lib3. And in order for the interpreter to resolve that, obviously you may want to install in your virtual environment, whatever you're working with Python, just invoke pip just to install that. What it's going to do, it's going to download that file, no matter which platform you're on. Whether you're on Linux, on Windows, or Mac OS, regardless of the version of Python 2 or Python 3, there's only one package that will satisfy that library. Obviously, that's not the case always, but I'll go into more detail later. So as I mentioned, same files and contents for every combination of platforms. What about C++? Do we have something equivalent? I would say yes. If you have a header-only library, the problem is simplified to an extent. So in this case, I have a code snippet that is using the cxxops header file. And that file is a single file for that library, and it will be exactly the same case. Same content, regardless of OS, CPU, or compiler. And how do you install this? And in my question mark over there, that would be our package manager, which could be any of these. It could be Conan apt, homebrew, VC package. And you would install it, and then here's probably the first difference, right? Just by calling that command, it's not necessarily going to cause the compiler to find that header. It will depend on what system you're on and how your system is or your environment is configured. You may have to, or someone may have to tell the compiler, hey, this is where you find that header. But that's a different story. But as I mentioned earlier, that case with Python was deliberately simple. The reality is that the Python interpreter can make calls to compile C and C++ code. We may all be familiar with this. The NumPy library is a good example because the C Python interpreter is written in C. Well, it can make those calls. That actually complicates the package story. So let's say I want to install a Python package that is compiled from C or C++ code. So in this case, leaf is an example. And then it's no longer the case that it downloads a single file depending on the platform. Now I have a very, very long list, and there's even more that obviously wouldn't fit on the screen. That would depend on which version of the C Python interpreter you're using, which operating system and version of the operating system you're using, the CPU architecture. So now we have more variability. The reality of this is that this imposes that the Python package manager now has to model a binary compatibility depending on the environment where the developer is working on. And also, when developers are working on platforms that were not considered when generating and uploading those binaries, it needs to have the logic to be able to build those from source. And that brings into the question, well, what is the format a Python source package, what format should it have for it to be built from source? And then that leads to something like this, which we all may be very familiar with, a xkcd. Different interpreters, different Python package managers, different Python package formats, different Python build systems. So the reality is, like, it wasn't that simple, was it? Going back to the first question of, oh, I wish it was like Python. There is a lot of complexity whenever there are binaries involved. So how about the same case in C++? We have a library that has its sources. It has public headers. The public headers are going to be platform independent, but the compile part of that, so what I'm calling the library binaries here, those are going to be different depending on, well, the compiler, the version, the C++ runtime as well. We'll get into that later. So, for instance, I may be working on Linux. I will get different binaries, or actual zeros and ones that will be different depending on whether I'm using GCC 11, GCC 13. Maybe I'm using clang with libstdc++, or I chose to use libc++. All those actual binaries are going to be different. So if we start sort of gathering our wish list for what a C++ package manager should do, probably one of the very first things is like to be able to model binary variants depending on some inputs, right? And these inputs are likely to be, like I mentioned, the operating system, the compiler version. We do have more variability as well. It's not just those. So for example, OS as CPU as well, we may have a library that you can build for Windows, for macOS, for Linux on 3 different compilers, 4 different compilers. So all the variability, ideally we would support it. Not all of the package managers that developers use support all 3 platforms at the same time. So that's something to take into account. But those are not the only sources of variability that we can get. We can get the build type. And this is just an arbitrary convention of, compiler flags. A release binary is one where it's optimized to a certain level, and I may or may not be defining the ndebug macro. And a debug binary, maybe at the very least, it contains debug symbols with the -G flag. Maybe we'll define a macro, or maybe it will be optimized with -0. It obviously depends. So it's an arbitrary convention. So that's just one example. Another example that's perhaps has more weight is whether a library is compiled to be static or shared library. So we have even more binaries for the same library, right? And that imposes even more constraints or more requirements onto our C++ package manager. We need to support multiple platforms. We need to support maybe optional features. So I just couldn't keep growing the graphic. But what if you can compile? OpenCV is a good example. You can choose between like 3 different threading models, I think. So those would be leading to different binaries for the same library, for the same version. How do you expose that to the user, to the developer? I want this one with TVB instead of using the pthreads library, for instance. You may want as well, and I didn't mention it here, obviously a different version, and by that I mean built from a different version of the source code, would lead to a whole set of new binaries. So in a world where you have all of these binary variants for the same library, maybe for the same version and on the same system, how do you model binary compatibility? You may be working on your project as a consumer. You have a library dependency, and you have multitude of library variants that you could potentially choose from. So I have 2 examples here. One of them is I'm working on Linux, and my program here, I'm working on debug. At the very least, I want to be able to debug my own program, and obviously we can cross out Windows binaries, macOS binaries, or I think for a different architecture as well. So I forgot to mention I'm working on ARM, right? So the binaries compiled for Intel, I don't need them. So of the 3 that are actually compatible, which ones do I choose? Well, the one in green matches exactly the configuration that I am working with. So I could say, okay, my project, I'm building C++17 in debug. Maybe I want my dependencies to also be built in C++17 and debug without any optimizations. But I also have the binaries built in release mode, and those are also, for variety of reasons, they're also compatible. Which ones do you choose? And then I'll explain later which ones you could possibly choose. Now, we may have a similar thing on Windows, where, as you know, the recent versions of Visual Studio, they have remained backwards compatible. So you could be working with Visual Studio 2019 and linking against a library that was built against Visual Studio 2017. That didn't used to be the case. Probably at some point, Microsoft will release a break-in version of the C++ runtime, but at the moment, that's the case. So here you may have a clear preference. Hey, if I have the ability to choose, well, I want my dependencies to be built with the same version of the compiler, right? Now, unfortunately, there's no solution that fits everyone. Some developers may very harshly prefer everything to be built exactly with the same configuration as you are working yourself, while others may think, okay, you know what? I'm working on debug, but I don't want to pay the price of the performance cost of all my dependencies also being built without optimizations. So what developers actually want, and this is what I got, is they want to be able to choose rather than these sort of imposed constraints, right? We have some cases where the developers don't necessarily have the ability to choose. A sanitizer build, for instance, and I think this is from the documentation of the memory sanitizer. It just specifically says it's critical that you build all the code in your program, and they also mention including the C++ standard library, which is sort of a tall order, with instrumentation. So you may be on Linux, you may be using perhaps the Ubuntu Debian app package manager. How do you even think of building all your dependencies coming from there with the memory sanitizer flag that you need to pass to the compiler and the linker? So this is an example where you may actually want to ensure the same configuration across your entire dependency graph. Another one, a simple one from Visual C++ as well, is if the C++ runtime, it's an obvious one really, should match the one that you're using with all your dependencies as well. And they have different options. So that comes from the Visual C++ documentation. And one that happened maybe, I think it's about 7 years ago now. I think it was GCC 5.4, if I'm not mistaken, around that time. They made a change to the C++ standard library where it was using an updated API to be compliant with C++ 11. So it wasn't necessarily a breaking change because the new version of the library contained the symbols from both before and after the change. So the same library could still satisfy both cases, but it did cause incompatibilities. So you had to make sure that things were built with the same API mode. So, and what they do specify in the documentation, if the third-party library cannot be rebuilt with a new API, then you have to recompile it with the old API. And I think some of you may have seen the, well, there's errors related to std::_CXX11. So we're back to the same problem that we had in Python is we may want to be able to build this from source. So a lot of developers may prefer, oh no, I want my package manager to give me the binaries. I don't want to spend time building them. But sometimes you don't have a choice. So going back to our wish list, we want to be able to build dependencies from source, and that's where we're going next. So we have a lot of resources, and then we want to get binaries at the end of this. And in the middle of that is an ecosystem of multiple build systems. So unlike other languages, the ones that I mentioned at the beginning in the first slide, there's no standard C++ package manager. There's no standard C++ build system. There's no standard interface to the existing C++ build systems. So that makes it really challenging to actually abstract this away. So between those things that I mentioned and the compiler and the linker and maybe the assembler and other tools, there's a build tool. It could be Makefiles, it could be Ninja, it could be MSBuild, it could be the Xcode build tool. But these days, I think developers are more exposed to CMake or Maven or things like that. So let's say we are in that space where, I need to build from source, release versus debug. I have to enable sanitizers. I have to change the C++ runtime, or I have to make sure that the library is either share or static. What do I do? And then this is a very simple examples. If you're using CMake, well, there's a CMake build type variable that it will read from, and then it will generate or pass along the correct flags to the compiler and the linker. But if you're using autotools, that's not so simple. Autotools doesn't really have an abstraction for this. So you have to use the environment variables that it reads from to pass to the compiler. And you get to decide, you're more exposed to which flags you're actually passing. So there's no abstraction really that means, oh, this is the build type. You just have to do it. So this is actually one of the challenges that we have in C++, is there's no harmony in how to interface yourself as a user even with these build systems. Static versus shared, again, another simple example. CMake has this variable that controls that. It's always bothered me that a lot of the CMake variables that are global start with CMake underscore, but this one doesn't. Start with a bit of underscore. I never understood why. Could be legacy reasons. But if we go to autotools, then we actually do have some flags and some abstractions, and they're typically very consistent with this. Is enable shared and enable static. In these cases, it can be both in the same project. With CMake, you typically, by default, get to choose between one and the other as well. So even the conventions of how the projects are structured are influenced by the build tools. So which makes it really difficult to maintain a package repository, by the way, which I'm not going to talk about today, but that's a different story. So going back to this, one of the biggest challenges that we face, and one of the reasons that this magical tool is difficult to engineer, is because there's no standard input. First of all, there's no standard build system for C++. There's no standard interface to the compiler even, obviously. The standard is limited to the actual language, right? And these tools in that big box in the middle, they keep evolving. The conventions of CMake keep evolving. You may have heard about modern CMake in the past several years. So it's difficult to catch up as well. So if we go back to our ideal C++ package manager, we have even more constraints now. It needs to be able to support building things from source for multiple build systems. And one of the compromises that you may make is, okay, I can support them all by expressing the instructions to build a binary with scripts. It could be Bash, it could be PowerShell, but the problem is that those are not platform independent, right? So then that comes in contention with the multiple platforms one. I think I have seen, I think it's Conda, and I don't know if it's still the case, where the build recipes is basically two scripts. You have to write a script for the Unix-based systems like macOS and Linux, and you have to write another one for Windows. So that actually creates a bigger burden on the maintainers of those recipes. And one very important thing is this needs to be repeatable. If you're going to have multiple developers across different machines building libraries from source, it's unfortunate, but it happens that you may be getting different results depending on the system, because a lot of those build systems perform introspections to see what's installed on your machine to actually decide what they build. So believe me, it's not really that fun to troubleshoot those problems. Another important feature to consider when it comes to designing C++ package manager is how to propagate usage requirements. And this means that we actually have to work with those build tools, those build systems as well, in order to make sure that the right flags get to the right program. So the typical build process is going to involve invoking the compiler, invoking the linker, which may be invoked by the compiler, and also eventually run it. And this is very important because sometimes we sort of stop off, okay, I have a successful build, but actually presumably you want to run your program. And if you're the developer of a library and you don't necessarily have a program for the end user, at the very least you have tests that you have to be running, right? So this becomes important. And if you don't have tests, like please write tests, very important. So here's an example. We have a consumer application. So I'm a developer. I'm only concerned with this application. I use dependencies, but I don't develop those dependencies. And I'm calling functionality that is implemented in libfoo, which is a static library. And that one in turn depends on libbar, which is also a static library. So because those two are static libraries, the linker is not involved in generating them. The compiler will produce an object files that will be bundled into an archive, but that's about it. But when I link my executable, then I need to be aware of both libfoo and libbar at link time. Even if my program as a developer, I don't even know that libfoo is using libbar, the linker there is going to have to know. It's going to have to know where to find it, because otherwise you're going to get undefined references for the symbols of libbar that are required by the translations units from libfoo. And then at runtime, because the executable has its dependencies linked statically, then it's not going to require those two. But what about a different case where the two dependencies are shared libraries? And in this case, the linker is involved. When you generate libbar, I'm assuming it doesn't have any other dependencies. We can assume that the standard C++ library is implicitly linked. When you generate libfoo, the linker is going to want to know where libbar is. And when you generate your consumer application, when you link it, as I mentioned before, you only know about libfoo, and the linker still wants to know where to find libbar regardless. And in this case, is a different flag, but an important one to take into account. And this behavior here is actually not, it doesn't happen across all the linkers. The default linker on Linux will require this, and I think others, and if you were in Victoria's talk this morning, LD doesn't require to know about libbar. On Windows does not require it, and I think on macOS it's also not required, but I could be wrong. So that's something to take into account, because some linkers still do. And at runtime, you are going to want to locate both libraries, regardless of whether you knew about them or not. Now let's complicate this a little further. Now, libbar is a static library, and libfoo is a shared library. So what's going to happen is that same as before, when I generate libfoo, I need to tell the linker, okay, this is where you find libbar, and then the object files from the libbar static library are going to be embedded in the actual shared library that's produced by this command. And in this case, when I produce my consumer application, I don't need to know about libbar. This is already sort of very well hidden inside of libfoo, and this is not needed neither at link time or at runtime. So you only need libfoo. Now let's make it even more fun. In the next slide. The idea here is, like, as you see what the commands are doing in all these stages, it changes depending on the type of library that they were. Your code is still the same. Perhaps your build script is still the same, assuming that that's CMake. All you have to do is tell, my application is linking against libfoo, and you have no visibility or awareness of libbar. But still, something somewhere needs to tell the compiler and the linker when producing all of those three things. And this may be across different build systems. Those libraries may have been built in different computers other than yours. Somebody needs to do this right at the same time. And for me, this will be a requirement. Keep this simple. We often see sort of build scripts that start trying to guess how things were built, rather than know the information by the package manager, for instance. They will try to see, was this a static library, was it not? And then the logic goes from that one line to maybe a 1,000 line find package script in CMake. We've all seen this. I'm not talking about Boost, but maybe I am talking about Boost. And as I mentioned before, because these things are built independently, they could be used in completely different build systems altogether. If we were in CMake land, and all of those were CMake, we could be taking advantage of modern CMake configuration files that are generated when you build those libraries. So those libraries would come with files that tell you eventually, help CMake determine which flags to pass to the compiler and the linker. But sometimes the idea doesn't exist, and those libraries are not using CMake at all, are not generating those CMake files at all. So we still need to know. Now let's complicate this a little bit, where we're still in the same case as before. The libfoo is a shared library, libbar is a static library, but now my consumer is independently of libfoo is also using libbar. So what happens here, and obviously the linker flags are going to be like that, is that at the very least, parts of libbar now are going to be present in two different places. libfoo is going to have binary code from libvar inside the libfoo file, and my application is also going to have binary code from libvar inside the linked executable. This could be a problem. If there are different versions, this could be a massive problem as well. If there's some global initializers that are in both places, this could be a massive problem as well. So, and you may not even be aware of these. The link time, they may happen at runtime, and it also nothing may happen at all. If they were exactly the same version and you have exactly the same objects maybe in different places and there's no global initialization, maybe everything will work fine, which you don't really want to get there and sort of take it to chance, right? So, oops, let me see here. And this is something I will go into for. It's like a great number of compiler and linker errors have more to do with how the dependencies were built and how they're managed, rather than anything that you have to action in your own build script. So from a productivity standpoint, you don't want your developers to focus on things that don't concern your own project, right? But they have to. They're going to be exposed to this, and I'll show an example right now. This was published on Stack Overflow, if I'm not mistaken, 2 days ago, where a user says that they're Javascript project. They're trying to use MySQL, I think it's MySQLite as a dependency, and they get a linker error when they link it. So let me show you the linker error. There are two things here that the person that replied to this to the Stack Overflow question actually noticed right away, and that's having really good sight. The compiler that they're using is the C++ executable from the MinW environment, so that's GCC actually on Windows. But the MySQL library that is getting passed to the compiler and the linker actually lives in a directory called VS14. So what's happening here, or allegedly happening according to the person that responded, is that you are in the MinW environment where everything is built with GCC and has a different runtime, but you told the compiler and the linker that there's a dependency that was actually built with a different thing. So the problem here is that from the developer standpoint, the actual error is you are using a dependency that doesn't match the C++ runtime that you're using. So this MySQL binary was built with Visual Studio, Visual C++, but your application is being built with GCC from the other environment. This would be possibly a user-friendly error if they know how to resolve a situation. What the user actually see is this, right? Undefined reference to check, and then a lot of symbols from the standard library. So raise your hand if you have dealt with those errors, or someone in your team, and you get like, so it happens, right? And if we had a really good system for this executable that the user was trying to build, the solution probably is not in your own code, and most likely it's not in the build system, and it shouldn't be in the build system, right? So think about this. All this problem is caused by something that has nothing to do with what you're doing, and it's really frustrating. So we've all been there, and now it's time to add more bubbles to our ideal package manager. So package manager should have enough information and interface with the build system so that the correct flags are passed to the compiler and the linker. It should have an awareness of symbol visibility, or whether symbols are being repeated in different parts of the dependency graph. And I know I already mentioned it before, but it needs to support multiple build systems because they are the ones that actually pass the flags to the compiler and the linker. Another section, how much time do I have? Perfect. Okay. No, we're good. We're good. Local shared libraries at runtime. This is going to be a fine one. So let's say that we've solved all the problems and we actually get it to link without a wall of linker errors. We're happy. And now we need to run. And this is what we get if we're on Linux. Fun thing, if you're on Windows and you have missing DLLs from invoking a command on the command line, it actually doesn't show any errors. If you double click on the program, it will show you a prompt of which DLL is missing. But I was sort of racking my brains the other day with an error that I couldn't really see. Anyway, this is not a happy place because we have a successful build that we cannot run. So this is quite confusing. So what are the different approaches that we may find here? Now we're dealing with a different beast altogether. We're not dealing with a compiler. We're not dealing with the linker as we commonly understand. We're dealing with the runtime linker or dynamic linker, depending on the platform. So now, depending on the approach, we have to tell that runtime linker, the one that actually launches our executables, where to find these libraries, right? So we may be, and then depending on which solution, we're going to have to take these things into consideration. The relocatability of the binaries, in case we want to build them on one computer, distribute it to another computer, or build them in one location and put them somewhere else, whether we want to or not want to have multiple versions coexisting. Use case, for instance, maybe there's a version of your code that uses OpenCV 3, and then you're testing OpenCV 4 in a different branch, but you cannot have both of them installed on your system, depending on what system you're using. The ability to write in system locations, if you want to rely on the linker looking in the default locations, and things like this. So let's go with one approach, is that on all platforms, and there's two environment variables at the top would be for Linux and Mac OS, and the one at the bottom would be for Windows. You can actually tell the dynamic linker, okay, this is where you should be looking for libraries. So that tends to work. But then again, do you want your developers to do it manually themselves and dealing with environments in the command line? How do we solve that, right? But ideally, your package manager is handling this for you. Another one is relying on your build system, and if you're building things locally in your machine and you want to run tests, and that's only going to work on Linux and Mac OS and other Unix-based ones, maybe you can use RPaths, right? Which is in your executables, at the very least, you can embed in your executables the location of where the shell libraries are. CMake does that for you by default, unless you are calling CMake install. In that case, it assumes that that they may exist in a fixed location. But then again, this may or may not work depending on whether all your shell libraries are in the same folder, in different folders, which version of a Linux distribution you're using, because sometimes there's two, I mentioned two tags in the ELF binary format, RPath and runpath. They don't behave the same. It's quite frustrating as well. macOS is actually a bit simpler. So you basically tell your executables, this is where all the shared libraries are, and when you launch them, hopefully everything will work fine. Another one is, the linker, at least on Linux and macOS, it will look in default locations. On macOS, forget about it. You cannot actually modify any files in those locations anymore, except for user local, I think, which is where Homebrew actually operates on the Intel Macs. But user lib, you would need administrator permissions to touch those locations. And then again, those locations are protected because they're managed by your distribution package manager. So this is managed by the maintainer of your Linux operating system, and maybe by the system administrator as well. So one approach that we can see if you're only working on Linux is that, well, you know what, I'm using different versions than the ones installed on my system, but the linker is still expecting to find the libraries in those locations. So I'm just going to launch the process by using the Linux kernel to tell my process, you know what, the user lib is different than what's in user lib of my system. And that's how you end up with an entire Linux distribution in a Docker container, which is actually valid if you're only working on Linux. But if your program or what you're developing is cross-platform, then, well, that's not going to work for Windows or Mac OS. And I'm always amazed by that approach. It's just like, let's just throw an entire Linux distribution file system and lie to the process, and it will find the libraries and it will actually work. And that's how the cloud operates these days. So that's pretty cool. So we have more requirements to a C++ package manager. We need to help the runtime linker locate libraries, and we need to, at the very least, be able to deal with relocatable binaries, whether they're built on the same machine or not. So dealing with trivial binaries, right? And I mentioned one of the things that I mentioned for C++ package manager is to model the binary variant that when the user installs something, how do they express what configuration, what operating system, compiler, architecture matches the binaries that they pull, right? So let's say you're on an Ubuntu Linux, right? This is all abstracted away from you just by the code name of the Ubuntu version. So when you do apt-get install leave OpenCV core, for instance, if your app is configured for Jammy, which is Ubuntu LTS 2204, if I'm not mistaken, that would mean that it will be obviously Linux, it will be GCC 11, and it will be compatible with the version of the standard library that comes with GCC 11, right? And the one thing that you may have control is the architecture as well. It supports installing binaries from multiple architectures in case you want to cross-compile as well. In this case, I was working on ARM, so that's why we have this here. What about if you want binaries built with GCC, let's see, 13? You would have to, maybe you could try, by the way, on that version of Ubuntu, you could try changing the keyword to the new version of Ubuntu and completely break your system, right? So the other alternative is that you would have to build those yourself rather than rely on the app package manager. So what that approach works really well. The reality is that there are some constraints. It's easy to install packages. There are compiled binaries that you can just download. All the versions are known to work well together and also known to work with the version of GCC that you have on your system. That's really good. But if we go back to those other scenarios where you may want to build things from source, maybe and do a sanitizer build, or get a different version of a particular library that is not the version that the LTS ship with. If we want to support all the operating systems because you're a developer of a cross-platform project, then that solution may not necessarily satisfy all of your requirements. So what we have, and the C++ is so complex in this sense, is that we have really good solutions to only parts of the problem. You may choose to actually build from source rather than distribute binaries to our users. This solves some of the problems as well. We may be able to support multiple platforms and not just be specifically locked into a Linux distribution. This also has the advantage that the binaries that are built, they will be using the compiler and the C++ runtime that is installed on the developer's machine. So you know they match in case you are in an environment where that's important to you. But obviously one of the biggest downsides is build times. If you have small dependencies that don't take too long to build, this may be fine. If you throw Qt and OpenCV and Boost into the mix, then you may be dealing with I don't know, hours. It really does depend on your project. So as I said, this could be really good in only some scenarios, but little. So, and one thing that it may be a risk or not, depending on the tool that you're using and the things that you're building, is, as I mentioned before, you may get different results in different systems, or different results on the same systems at different times of the day or the month or the week, because those builds actually perform introspection on the system and will generate different binaries. So now we have more things. If we're dealing with binaries, you may want to, and building them from source, you may want to distribute them, right? You don't want to build them from source all the time, although some projects, that's what they actually do. Instead of dealing with a dependency manager, they just embed or fetch the code, the source code of the dependencies into the project, right? Which means that they will actually be building that time and time again. You may want to not do them and then do binary caching at the very least on your own system. You may want to build them on CI and distribute it to your distribute the binaries to your team. In that case, yes, you need to be able to have a server to host the packages and distribute them. You may want to do press building to different platforms. You may want to be able to sort of have a traceability of the project dependencies because you have to do an audit as well, maybe for compliance or for security audits and things like that. You may want to say use you can decide whether your project only works with one specific version of a library, or you can say, no, actually, I do work with Boost versions 172 to 182, for instance. And in that case, if you have that level of using version ranges, you're probably still going to want to have a mechanism to have repeated builds, because if you're using the version range, you may resolve to one thing today and to a different thing 2 weeks from now. You might want to have extensibility and customize certain behaviors. For instance, what I mentioned before, where some people really want everything to match the same compiler, and others is like, I don't care, give me something that will get my linker to and my applications to run. You may want to support package signing if you're actually distributing the packages. So we're dealing with a lot of requirements, a lot of constraints. So what I say when people say, why do we not have a package manager like other languages, is because we want everything, and sometimes we want conflicting things. But us being from the Conan team, we like a challenge. So I would like to say that a lot of these things are supported by Conan. You do have control and flexibility to do many of these things that in the past were considered impossible or not necessarily promoted by some of the existing solutions. So I think that's it for today. Thank you very much. Any questions? Yes.
You do kind of additionally certain library that is inside of the Conan any participate on the main. And use it. It's not working with exactness. It would be in the direct domain connection goes to main depends.
Yeah.
To report pieces,
Sorry, so let me repeat the question so everyone could hear, and if I understood correctly. You're using a dependency from, I imagine, Conan Center, and something is not, you identify a problem that's not working correctly. You should report that to the Conan Center issue tracker. And if not, sometimes there's a really active community. A lot of the contributors to Conan Center also monitor the CVP line Slack. And there's the Conan channel as well, and some people in our team as well. So either will be a good place to start.
And the second question: how easily is it the aim that using the compiled version to, let's say, force Conan compile everything from the source exactly possible?
I see. So your question is how easy it is to sort of decide to not use a precompiled binary, but to use Conan, right? So, and to force the libraries to be built from sources. When you call Conan install and there's an argument --build, you can specify the names of the things that, and Conan will say, okay, I will build this. Even if the binary is available either remotely, it will rebuild it. And if you have libraries where you want that behavior to be the default, there's actually an attribute that you could put in the recipe that it will force all consumers to always build them from source. So it happens quite frequently that we get requests for, I have this library that has embedded absolute paths in the actual binaries that then at runtime it's going to expect things in those paths. It would be really helpful if everybody that downloads the recipe, they are forced to build it from source such that guarantees that the paths exist in their machines. That's maybe typically the case for a build tool or something like that, but we do have that attribute where you can force this rather than rely on your user to pass a command line argument every time. Anything else? Nice. Well, thank you very much. I do have one small announcement: is that the closing message has now moved to room 11 instead of this one. That's it. Thank you.